Hello, everyone. I can't, well, 60 already. Hello, folks. We are already screen sharing, so I can't see all of you, but that is okay. That's on purpose. Good to see some familiar names and some new names as well. Welcome to our Bash in the Eclipse after the bell tonight. My name is Emily Vetney, and I work in advancement here and alumni services at Wabash College. And I want to thank you for being here and also introduce our two guest stars tonight who are going to teach us all, at least in my case, the first science class I've taken, thank God, in like 10 years. So Professor Colin McKinney is an associate professor of math and computer science here at Wabash, and he's been teaching here since the fall of 2011. He teaches courses in math and computing, but also cooler sounding ones like ancient Greek math and spherical trigonometry. He also loves video games and is originally from Texas. And Dr. Gaylon Ross is in his 6th year with the physics department at Wabash. He is an associate teaching professor of physics, and his doctorate is from Notre Dame, which is in my hometown, which I just am now learning, and I think that's cool. He studies the study of reaction sequences in hot stellar environments like the cores of supermassive stars, which I assume we might learn about tonight, and is also a native Southerner. He is from Arkansas. Before we turn it over to the professors, though, I'm going to turn it over to Ron Dostal, our Director of Alumni Engagement here at Wabash, class of 92. I think I misclassed him at a couple events ago, so I want to make sure I get that right. Enough from me. Ron, take it away, and then Ron will turn it over to the professors.
Thanks, Emily. Appreciate you hosting tonight, and thanks to Professors Ross and McKinney for doing this. Thanks also to all of you who have joined us. We do these after the bell, and in some cases, Wally's Bookshelf sessions, more or less monthly. And hopefully you like this one and come back for more. We've had basically record registrations for this session. It's obviously very timely, so we're excited to be talking about it tonight, and just watching the folks kind of roll into the waiting room. I think it's safe to say that our attendance tonight has eclipsed all of our other after the bell sessions. So with that, I will turn things over to Doctors McKinney and Ross.
Thank you, guys. We appreciate it. This is Gaylon Ross speaking right now to you live from Goodrich Hall. I really liked the being introduced as a star of the evening. I thought that also could, really fit the theme for tonight with talking about the sun. But we'll stick with professors. We're talking about the great American eclipse of April 8th, next Monday. And I can tell you, as someone who started teaching 31 years ago, astronomy, in fact, 31 years ago, that I could point to this eclipse as something that I looked forward to in the future. So to say that I've been waiting on this for a long time is not an overstatement at all. So we look forward to telling you a little bit about eclipses overall, about this specific eclipse. We will be taking questions throughout the discussion tonight. I will probably be kind of focused on the screen very much and what we're saying, but we'll have our moderators help get questions out to us. So feel free to ask as you go along, or we'll have some time at the end. Dr. McKinney's going to do, I'm going to do a lot of the things that look like what a professor would do, give slides, tell you some facts, and then Dr. McKinney is going to do some really cool things with simulations and some things that are more related, say, to historical or classical aspects of astronomy. So without further ado, this is the path of the great American eclipse, and you can see the times on here for the eclipse. San Antonio is going to be at about 1:32 p.m., Austin 1:36, Indianapolis 3:05, Toledo 3:12, Cleveland 3:13, Little Rock near my old hometown 1:51. But notice this jump here from 1:51 to 3:05. You might think, wow, that's a pretty long time, but remember, we've changed time zones. So if Little Rock were in the same time zone, that would be 2:51 compared to 3:05 here, only about 14 minutes. This eclipse, the shadow that we're talking about moving across the US, is zooming by at about 2,000 miles per hour. and it's only a little over 100 miles wide, around 110 or so approximately. So you have to be, as you can see from this map, you have to be fairly lucky to be in the path of this particular eclipse. Overview of the talk tonight. We're going to talk about shadows and causes of eclipses. We're going to talk about types of solar eclipse, specifically those. I'll do a little discussion of lunar eclipses. We'll talk about eclipse seasons and the fact that we've been able to predict upcoming eclipses for thousands of years. And Professor McKinney is going to wow you a little bit on a mechanism that demonstrates just this. And then we're going to focus on the Great American Eclipse, all the different things associated with this. I'll show you an interactive Google map that I assume most of you do not live right here in Crawfordsville. You can use this map to actually go into your backyard and find out exactly what time things are going to occur for the eclipse in your area. We'll talk through the different events like first contact, second contact, and so forth. And then I'm going to wrap up with some safety reminders, because it is very important that we protect our eyes during this process. So first of all, what we've got here is a sun, the earth, and the moon. These are nowhere near to scale. In fact, if we were to try to draw, use this size sun and an earth and a moon, we wouldn't even be able to see the earth and the moon. These guys are relatively the right size. Oops, let me go back. These guys are relatively the right size, but the sun is 400 times larger than the moon. So you ask yourself, well, then how can the moon cover up the sun? Well, the moon is 400 times closer to us than the sun is. So that ratio causes the ability for, if we're on Earth, we can see the moon block out the sun in the right conditions. So what we've got is, just imagine, again, every month, or month, because that's why it's named that, every month, the moon orbits Earth. Okay? So it's doing this sort of thing. Now you can see the shadow. There's two parts to a shadow. There's the darkest part called the umbra, and that's the part where if you were standing in that and tried to look back at the sun, you wouldn't be able to see it. You'd be completely blocked out. And then in this area right here, you have what's called the penumbra. And in the penumbra, if I were, say, in that area looking back, I could see part of the sun, but part of it's blocked out by the moon. So I'd see a little bite taken out. If someone were looking at you in this region right here, they would see you you wouldn't have a bite taken out of you. They just see that you weren't quite as bright. Perhaps not as bright as you were when you were a Wabash student or so forth, but different. Okay? So a solar eclipse occurs when the moon is blocking out the sun. Similar thing on the other side. When we've got the moon over here and Earth in this location, notice the Earth being 4 times larger in diameter than the moon, shadow goes out farther. Most of the time, the moon shadow actually can't quite reach Earth. The darkest part can't. But Earth shadow is always long enough to be able to cover up the moon. So these are the orientations you would get, and we'll look more at those in just a second. But notice if the moon were in this location, part of it is in darkness and part of it is getting a little bit light, less light than it would normally get, but some. So you'd see a bite taken out of the moon here as it moved into this region, completely covered up, moves back here, it's got a bite and so forth. And I'm actually doing this backward. It should be going around this direction, but so forth. So that's the geometry that we're dealing with here for these eclipses. So if we talk about a lunar eclipse, and I know that's not what we're interested in tonight, but we ought to know something about these, because lunar eclipses are much more readily seen by folks on Earth. One, there's a couple of reasons for that. One, when the moon moves through Earth's shadow is so much larger that it's much more likely that the moon is going to be able to move into that shadow and be eclipsed here. So we're only focusing on what we call the umbral part, the part where the light's blocked out. So you see a bite taken from it. So it's more likely that's going to happen. Secondly, to see the eclipse, you don't have to be in the path of anything. You just have to be on the side of Earth that can actually see the moon. So for any given lunar eclipse, half of the Earth, in fact, a little more than half of the Earth, because the Earth is rotating at the time, can see that lunar eclipse. This happens in a phase of full moon. Okay, so the moon has to be in a full moon phase and be passing through Earth's shadow at that point for us to see this lunar eclipse. And this is what these look like. Okay, so the moon would be over here, it would be somewhat in the penumbra, and then we start seeing it move into the umbra. There's a bite taken out, a little more of a bite. And then in this region right here, you can actually see the Earth's shadow forms a circle. This is evidence that Earth is actually a sphere, or at least very close to a sphere, because the only shape that will cast a circular shadow, no matter what its orientation is a spherical shape. So a flat Earth that's shaped like a coin, that's not going to cut it if the orientation is sideways. So, and this isn't something new. I'm not telling you something that wasn't known well over 2,000 years ago. Okay, so then the moon moves back out. There is something, though, that you ought to notice. We have pictures of the moon in here. We can see it. And I just told you that the light was blocked out. You're in here and there's no light coming through. How are we able to see this moon? Well, the answer is Earth has an atmosphere. Okay, so sunlight coming through Earth's atmosphere actually gets bent or refracted, and that orange or red light is bent perfectly onto the moon. The rest of the light is scattered out, blue light in the sky. But we see that like an orange sunset, you would see this sort of thing getting bent onto the moon, but it is about 10,000 to 500,000 times dimmer, depending on the conditions for that particular eclipse. Okay, so it's a fantastic thing to see, but most people, I would say, have seen a total lunar eclipse in their lifetime. Okay, I've seen a number of these, and total confession, I told you guys that I'm looking forward to this eclipse and have been for 31 years. This will be the first total eclipse for me. I have been in 90-something% totality 3 different times. I have yet to be in totality. I'm looking forward to what that experience is going to be like. So if we talk about solar eclipses, what do we have? Well, here's the sun and there's the moon, and we're going to talk about those 2 parts of the shadow again. You got an umbra right here, and then we've got that penumbra. Again, if you're in the umbra, you can't see the sun at all. I can't see any of it peeking back. So at position 1, I'm right here. I can't see the sun at all. At position 2, I'm looking back toward the sun. The moon's taking a bite out of it. Okay, notice I can see the sun, though, over on this side coming to my location. If I'm over here at position 3, I look back, I see the moon or the sun peeking out from this side from the moon. Okay, if I'm even perfectly in line, though, if the moon's shadow doesn't quite reach all the way to me, if the umbra is too short, then what we end up having happen is I'm back in this area right here. I end up with a ring. I can see the sun all around the moon here, forming this ring. These are called annular eclipses, or sometimes ring of fire eclipses. This is the kind of eclipse that actually occurred last fall, last October. It was during our fall break here at Wabash. If you were out on the West Coast, you could see this, but it never got total. It was never totality. So when folks were watching this eclipse, it was a fantastic thing to see, but they still had to keep their eclipse glasses on because there's still enough of the main body of the sun peeking around all sides that it's just too bright to look at. Okay, so if we look at the sun, moon, and Earth, this moon phase that occurs is called new moon. Okay, it happens every month, every 29.5 days. This occurs, but we don't get an eclipse every 29.5 days. One of the reasons is that the moon's shadow, the moon's path around Earth is elliptical. It's oval shaped. So the moon, most of the time, in fact, the moon's average distance from Earth is a little bit too far away to actually reach cause the shadow to reach Earth. So most eclipses can't be total, even if the alignment is perfect. They can only be annular, okay? But because it is an elliptical path, at other times during that new moon phase, the moon could be a little bit closer, and then that causes the shadow to strike Earth. And in that situation, if you think about it, the moon moving farther away from Earth means that the shadow may not reach at all, or if it does touch, the spot's smaller. If the moon's closer, then that spot that's going to move across the Earth, that width of the path is going to be larger. So we're in a spot right now, no pun intended, but we're in a time right now where that spot is going to lead to a path that's about 110 miles wide, something like that. Professor McKinney, I think, is going to move forward with us right now and show us a little bit of this view with a simulation that he has. So I'm going to hand it over to him, let him share his screen, and then you're going to get to listen to his dulcet tones for a few minutes.
Okay, so Dr. Ross is going to unshare his screen. I'm going
to stop share. Yep.
And then I'm going to share mine, and we'll start with this one.
Okay, I'm going to jump in really quick. I put it in the chat, but I just want folks to know, please feel free to type any questions or comments in the chat. The professors gave me the go-ahead to stop them if something comes up. So please be putting things in the chat that you find confusing or interesting or cool, and we will get that answered.
And so I'm not looking at my screen or my webcam. I'm looking at a different computer. I'm doing this with two. So what I have here is a piece of simulation software called Universe Sandbox. And what I'd like to kind of start to do is talk about the configuration of the solar system generally, but then also concentrate on the specific part that we're dealing with. Okay, so here's the sun. Yay. You all know that. And here are the planets. And I'll kind of rotate it so that we can see the Earth. And then, of course, we've got the moon around it. We'll zoom in on that in a moment. And all of these, the planets, as of course we know, go around the sun. But what I want to do is kind of get down this view here. And I know there's a lot of lines going on here because what I've had the software do is show you the sort of orbital path relative to all the other orbital paths of the planets. And in particular, you'll notice that all of the planets, their orbits are not perfectly in the same plane, but pretty close to the same plane. And we call this plane, the plane that the Earth's orbit goes through is the ecliptic. And we'll see that in a moment on a different piece of software. But all of the orbital planes are roughly the same. The one exception to that is Pluto, but it's not a planet anymore anyway, so who cares about it? Okay, so if we look here at Earth, and I'll zoom in on Earth, then of course we've also got the moon around it. And what I want to do is I'm going to kind of look at, let's put ourselves back on the plane of the Earth's orbit. And if you notice this sort of line right kind of starting here and going across the mouse cursor, that's actually the orbit of the moon around the Earth. And you'll notice that that orbital plane is not the same as the orbital plane of the Earth. If it were the case that the orbital plane of the moon was exactly the same as the orbital plane of the Earth, then we would basically have eclipses every month. And that would be really, really cool. Unfortunately, the moon is tilted slightly at a 5-degree angle. So what has to happen for an eclipse is, of course, as Dr. Ross showed you in the previous diagrams, the Earth, moon, and sun all have to be in line. But there's one more condition, and this is why it's more rare, is that the point that the moon is at along its orbit, if I zoom out just a little bit, is what we call either an ascending or descending node. So the Earth's orbital plane, let's just think of that like a table, and the moon's orbital plane is tilted relative to it by, 5 degrees or so. And each time the moon orbits the Earth, there are 2 points, and they're on opposite sides of the orbit, where the moon's orbital plane, or moon, goes basically from above the Earth's orbital plane to the below it. We call that the descending node. And then the one on the other side, where it's going back up the other direction, is the ascending node. So the eclipses, or total solar eclipses, can only happen when the moon is either at an ascending or descending node, and when all 3 of the bodies, Earth, Moon, and Sun, are in a straight line alignment, or syzygy as we call it. It's also, by the way, syzygy is a fantastic Scrabble word. If you've got a bunch of Z's and Y's and an S, you can just dominate. I have yet to be able to play that in the game, though. Okay, so that configuration is, I've got the software basically loaded up for 12:17 p.m. next week on Monday. And if I come over to the Earth, and we sort of, I'm going to put the sun behind us, and I'm going to start to move time forward. And what we're going to see is right there, we've got the shadow, and I'll pause the simulation here. So this is the beginning of the eclipse, and we can see the eclipse moving from west to east here, basically as the Earth is rotating. And if we move it forward a little bit, then sort of right about here is when it'll be here in Crawfordsville. Now, the resolution of the shadow, it doesn't, obviously the true shadow is not nearly as big as this. So it's not just depicting totality, and also I'm zoomed in on the Earth in as much detail as I can get with this software, because this software is actually designed for, well, I can zoom out and view the entire solar system and everything in the Kuiper Belt and then keep going, right? So this is kind of not the intended purpose for this this particular software. But that's basically the configuration that we would see. And if we kind of look back, and I'll turn off the orbital lines here so it's a little less messy, then we can see, and I'll just kind of tilt it a little bit, we can see the Earth, Moon, the Earth, the Sun, and then there's the Moon. And if I went so that we were all 3 in line, then we won't see the, obviously we won't be able to see it because the Earth's in the way, but that would be the point of where we would be able to see totality. And I do see a question.
Sorry, yep, what is the Kuiper Belt?
Okay, so it's actually spelled this way, Kuiper. So the Kuiper Belt basically are very far distant things in orbit of the sun, well beyond all of the planets. So let me turn back on the orbit so we can see them. But the orbit of Neptune, Pluto is out here, right? So this is way far out. Kuiper Belt stuff are things that are in orbit far beyond that, but that are still, in some sense, technically part of the solar system, but they're going to be very, very small bodies, asteroids, things of that sort. Yeah, it's, and then, you know, this is only showing sort of some of the biggest ones, but there are like probably thousands upon thousands of very tiny Kuiper Belt objects, many of which we can't see because they're so far out and so small that we wouldn't be able to see any amount of light being reflected on them, and they're too small to gravitationally influence any other body for us to kind of figure out that they're there, which is how the gravitational anomalies is how we, of course, figured out that basically all of the planets beyond Saturn actually were there, because they're too small, or they appear too small from naked eye, but their perturbations on causing perturbations of other celestial bodies, then do a bunch of math, you can figure out that there's something massive that's tugging on say Saturn or something.
Says the
Okay,
mathematician, by the way.
Yeah.
Yeah.
So And the math that you do for that is a lot of fun, but it's also really, really tedious, especially if you don't have a computer. Okay, so I'll quit the screen sharing here. Any other questions about the simulation, this simulation before we move on? Oh, and this, by the way, you can see there's Pluto's orbit, real tilted compared to all the rest of them. And then we've also got in here some of the dwarf planets. So Ceres, these are some of the, or that's not Pluto, the real tilted one. Pluto is, where is it? Here it is. But yeah, it's pretty significantly tilted relative to the ecliptic.
Okay, a question. Will JWST folks have any input and or observations?
I'll jump in on that one. I would doubt that they, first of all, the Webb is much farther out than Earth. So that's JWST for the rest of you. That's the James Webb Space Telescope, and it observes in the infrared. So first of all, taking a chance with it looking at the sun, for any amount of time is going to be pretty dicey because of the amount of light that could come in. There would be other telescopes that would probably turn toward it, but you have to consider they're not really seeing it from Earth's standpoint. So it's not an eclipse that occurs here on Earth isn't really occurring for other space telescopes, other observing sites in space. James Webb is doing a lot of incredible things, but this is one it's probably going to leave alone. But I'll dig into it more. If I find out differently, I will make sure and let you guys know.
And as much money as it took for us to get the thing up there in the first place, I don't want to have to send a replacement.
Well, yeah, it's not getting fixed if it goes down. So, Professor McKinney, if you could, let's see.
Stop. Okay, you should be good to go now.
I will share again. Okay, we're back. Okay, so this was the slide we were looking at before, and I'm going to give a little more simplified version of what Professor McKinney showed, just from like a slide format, because this is that 5-degree tilt that he was talking about. So if we simply consider, there's the sun, Earth. So Earth is making an orbit around the sun every 365.25 days. Okay, Moon is making an orbit every 29.5 days with respect to the sun. So because of that situation, then when we have these nodes that we're talking about, where if we looked across the orbit of the moon would take it such that it was either directly between the sun and Earth or directly behind Earth from the sun, those occur at certain times of the year, so-called eclipse seasons. And notice they're about 6 months. If you're thinking about Earth moving around the sun, they're about 6 months apart. So when you have these situations where you could have a favorable setup for eclipses, you could then have both a lunar eclipse and a solar eclipse within a few weeks of each other, 14, 15 days apart. Then you're going to have to wait about 16 months, about 6 months for that to occur again, except if they're not perfectly aligned. We'll explain that in a second. But at other times, because of the tilt of the moon's orbit, the shadows don't line up properly. The moon's shadow, even if it's long enough, doesn't strike Earth. Earth's shadow is above or below the moon. So we don't end up getting an eclipse. So there's only certain times of the year that you're going to get eclipses to occur.
Dr. Ross, we've got a question.
Okay.
For this eclipse, are we in an ascending? Oh, okay. There goes Professor McKinney in the chat. He wanted to know whether we were in an ascending or descending position.
Yeah, this one is ascending.
Yes, and what we got 6 months ago with the other was a descending. So if you think about the path that it came through, it came from the northwest down toward the southeast. This one that we're seeing it go from southwest up to northeast. So
yeah. And the eclipse in 2018, 2017?
Yes.
Yeah, 2017. That one was descending, and it went basically from the Pacific Northwest and then kind of cutting down a little south of here. Yeah, that one was descending. The one next week is ascending.
Right. And we'll see that. We'll actually see when we look at the path that it's following. You can imagine why that shadow then goes the direction that it was. I am going to add one other thing too while I'm thinking about it. Professor McKinney was talking about the shadow moving across Earth. Actually, what they were showing you there, it's hard because there's not a hard definition of the complete shadow or the umbra to penumbra. They were actually showing the penumbra there. So they were hitting this. That was the reason it was so large. It wasn't a glitch in the simulation. They're actually doing it properly. It was kind of cool. So everybody that was somewhat in the shadow was getting some eclipse, just not totality.
Yeah, and the other thing that shows though is that really the shadow is not moving across the Earth. It's more that the Earth is rotating underneath the shadow. And
well, the moon's moving a lot faster. The moon's moving a lot faster in front of the sun than Earth is rotating.
Yeah. Okay. Yeah. That's right. It's hard to visualize.
That rotation would actually be, because the direction of the rotation, that wouldn't be quite right either. It almost stands still if the speeds were the same. So, because we're moving along that, well, that's backward too. Anyway, let me go to this.
Yeah.
This is the eclipse. When we talk about eclipse seasons, notice that for a particular year, say we could go to 2020, there was a lunar eclipse, which is called a penumbral eclipse. The moon was in the light part of the shadow of Earth, which means it didn't even have a bite taken out of it. All it was dimmer. And as I like to say, this is the least spectacular thing you will ever see in your lifetime. I mean, all it does is look like a dimmer full moon. But as we go through, we see different eclipses that are occurring throughout those years. We had another penumbral eclipse, an annular solar eclipse, and so forth. So you can get multiple eclipses. Notice each year they've shifted upward a little bit. So they occur just a little bit earlier than they did the prior year. That's because it takes 29.5 days for the moon to get around Earth. And our average length of a month is only between 31 days, just slightly over 30. So because of that, we get a shift of about 11 days of when the eclipses occur. So they'll occur, particular kind of eclipses will occur about 11 days earlier the next year. It won't be the same exact eclipse. It won't occur in the same location, but you can kind of roughly set your watch by somewhere on Earth they're getting the same kind of eclipse, most likely. Okay. So this is the one that we're over here. There's April 8th of 2024, a total solar eclipse in Saros cycle 139. It says that the duration of the eclipse, 4 minutes and 28 seconds in North America. So for the folks that are in the ideal spot, if you're in the sweet spot of this eclipse, right down the center line, and at the point where the motion of the sun's shadow and the rotation of Earth and the curvature of Earth are just right, you get 4.5 minutes of totality if you're in that perfect spot. Let's see, let me close this out again. So just something to mention, even though we say eclipses are rare, most years have 4 overall eclipses, a mix of lunar and solar. You can get up to 7 total. But the majority of the solar eclipses that would occur would be partial. You wouldn't be exactly at that node that Professor McKinney was talking about before, so you wouldn't have perfect alignment. You only get partial eclipses. Oh, I think it's time for me to share again. So I'm going to stop sharing and let you take over.
Yeah, so the next thing I'm going to show you is this. Okay. So the word Saros that Dr. Ross mentioned actually comes from an ancient Greek word. It was a unit of measurement amongst astronomers, but it sort of re-entered into modern lexicon with Edmund Halley, after whom the famous comet is named. But anyway, so eclipse reckoning is a very old business, and it predates basically anything you might imagine. Ancient Greeks, Egyptians, ancient Babylonian peoples were well aware of eclipses. Heck, war stopped because of a total solar eclipse once. And they were actually pretty good and pretty accurate at predicting these things. And that's really quite interesting from a historical standpoint because, of course, the ancient view of astronomy and of orbital mechanics and cosmology was that the Earth was at the center of the universe and that everything else rotated around it. Of course, we know that's not the case today, but even with that mathematical model of the universe, you can still actually get very, very precise predictions on eclipses. So what I have here is a simulation of how we think this ancient device called the Antikythera mechanism works. You might have heard of the Antikythera mechanism if you saw the most recent Indiana Jones movie, where it features quite prominently as a plot device, although it wasn't a time machine. It's a machine that tells us things about time, but it's not actually a time machine like in the movie, unfortunately. So what this thing was understood to do, and we do have a little fragment of a thing on the side of it, which is maybe the oldest instruction manual, I'm not sure, but the only, of course, mild problem is it's written in ancient Greek, and so if you don't read ancient Greek, then you're kind of SOL. But what this thing was meant to do was to predict the positions of the sun, the moon, and the naked eye viewable planets, and also therefore could be used for predicting and timing out the eclipses. Inside this is a bunch of gears. The metalwork that would have been required to do this didn't see reintroduction into European kind of clockmaking and stuff until probably the 17th or 18th centuries. And I've configured this thing for the appropriate date of the eclipse, and I've got it at hour 19. But what you can see, of course, is, okay, the Earth would be in the center here, and then the moon would be this dot, and then the sun would be that dot. And I'm a little off on the time, but they're basically right in line. Well, eclipse. Then what you can see around the outside and inside these rings, these tell us two things. The innermost ring, okay, which has all of these names here, this is the zodiac ring that tells us basically the 12 zodiac signs and divisions of the ecliptic, and it tells us where the sun is in the zodiac. And you can't see it because the sun's representation is kind of covering it. But the word that's underneath there is krios, which means a ram, and better known to us today as Aries. And of course, that's exactly where we are in the zodiac. We're in Aries. And then along the outside ring, you have, this one's kind of a mouthful. These are Hellenized names of Egyptian months set down by Ptolemy III in the Proclamation of Canopus. So a couple of interesting things there, that these are really Egyptian names, but they're just written in Greek, and we're on the border in the calendar, the Egyptian calendar, of Farmuthi and Phamenos, and sorry, I have trouble reading ancient Greek upside down. But anyways, we're sort of right on the border there between these 2 months. And the other thing that's kind of interesting is all of these ancient Egyptian months were exactly 30 days, but then you'll notice there's this little extra little bit there, which would be the intercalendary part. So there'd be festivals and stuff there during that period of time. So ancient mathematicians, we're talking 2,000 years. The date on this Antikythera mechanism is, we think, somewhere between 150 and 100 BCE, roughly. There's still considerable debate about that, but we think, roughly speaking, that's where it dates from. would have been perfectly capable of predicting these things to pretty high degrees of accuracy using what we might consider today as limited mathematical tools. But they were perfectly able to do it. So this simulation is being run in Mathematica, and there's a web version of this. So if you just sort of look for the Antikythera mechanism simulation, then you'll probably find this as one of the first hits. And then you can change the dates, and you can also take away the box and look at the gears from to kind of see how we think it worked. The only problem with this thing is it was found on a shipwreck in a little over 100 years ago by some pearl divers off of the island of Antikythera in the Aegean. And Antikythera is such a small island that it doesn't even really get its own name. It's the island before Kythera, hence the anti part. So they found this thing. The Greek Navy dug it up, and of course it's been at the bottom of the sea for 2,000 years or so. So it's not really in the greatest shape. It's all corroded and barnacled and whatnot. But with X-rays and other techniques, we've been able to kind of peer on the inside and see things that are hidden. And there's pretty good reconstructions that have been done of this thing to figure out exactly how it worked, what would the metalworking have required, and so forth. And they even sell little reproductions of these in a museum in Athens, I'm told, for a few €100. So if you find yourself in Athens, make sure you go to the museums to see the pieces of it. I have yet to go, but I'm told it's really neat. Okay, so I will unshare here. And then, Gaylon, you can go back to the slides.
Okay, thank you. I'm sure that everyone else is in agreement with me that the only thing that we had difficulty doing, much like you, was reading the ancient Greek that was upside down. Other than that, looked like the device was perfectly self-explanatory. So it's a fascinating device, and the thing that we get out of that is that we've been able to predict eclipses long before you would suspect, and to a high degree of accuracy. Well, here are a couple of eclipses. We're talking about those cycles, that Saros cycle. This is the eclipse that we've got coming up next Monday, April 8th, 2024. So this is the path of totality that it's going to follow. The lines out to the side show you where the partial eclipses would occur, where the penumbra of the moon would come across. So notice 80%, 60%, 40%, and so forth. This is the only area where you get totality. These cycles occur. The reason this is so predictive is these occur in cycles. So this Saros cycle, the first eclipse in the cycle, actually, for it started, it was May 17th of 1501. It has repeated every 18 years, 11 plus minus 1 days, and 8 hours. Okay, you have to say the plus minus for the days because it depends on how many leap years are in there. So but the days are correct, 65, 85.32. The last eclipse in this Saros itself, because as the moon is orbiting around Earth, because that path is changing because of that tip, this one set of eclipses, after about 71 times, usually 71, 72, that eclipse is over, that we start a new cycle. But there are multiple ones going on at any given time. Well, the last one's going to occur in 2763, so make sure you're around to watch that. But notice every 54 years, so we're saying you get a similar eclipse every 18 years, 11 days, and 8 hours. That 8 hours is important because Earth rotates on its axis 24 hours. So that's a third of the way around. So the eclipse is going to occur somewhere else on Earth. You're not going to see it. But if you go every 54 years, that 8 hours turns into about 24. Okay. That 0.32, becomes 0.96. So we're very close. So 54 years and 34 days, the same approximate eclipse occurs in about the same location. So if we go back 54 years and a little over a month to March 7th, 1970, we see this eclipse right here. And I've spoken to a lot of people that remember that this was the eclipse, that kind of got them interested. In fact, the cover photo that we had for our on our slide today was taken by an astrophysicist who also is an eclipse chaser. This was the first one that he saw that really set the course of his life. So,
Dr. Ross, sorry, we've got a few questions.
Okay, sure.
Okay.
Yeah.
Okay. So, Steve says the Wabash campus is on the very edge of the path of totality. In recent days, the press has reported on updated models that have narrowed the path of totality because of revised estimates of the sun's diameter.
That's
Do
correct.
you guys have access to models that incorporate error estimates? And is there a chance that Wabash will miss out on totality crying face?
I've checked into this, and I don't. Even the new models still have us in totality. So we shouldn't have any issues with that. I'm keeping an eye on anything that I can see, but comparisons of those models to the simulation that I use didn't really change things enough for us to be concerned about. Wabash is still in totality, and we're going to show that later. We're going to get very specific into the times on that.
Okay, there's another question.
The other question, I can see it. Yeah.
Okay.
About how close to the sweet spot of 4.5 minutes is Crawfordsville. So we are very, very close to the edge of totality. We will only get about 50 seconds of totality, only of which 30 seconds or so will be safe for naked eye observation. And I'll let Dr. Ross explain why about that later. If those of you who, of course, been to Crawfordsville, which I assume is most of you.
The Athens of Indiana. So, I mean, we're back to Athens again. So.
If you go down the hill to all the hotels and stuff that are at I-74, you are outside the zone of totality, right? So we are like really just grazing the edge here, but we're close enough or far enough away from that line that I'm not concerned about the lack of totality. I'm more concerned about the weather, frankly. But yeah, the 4.5 minutes, you would have to go basically southeast from Crawfordsville, probably a few hours drive. Bloomington, or maybe an hour and a half would probably be good.
And if you get to Indy, you're good. I mean, you're going to be almost to 4 minutes anyway. When you get into Indiana, there's actually no place that's 4.5 minutes. This spot right here, this is when it's 4 minutes and 28 seconds. So down here in Mexico, the time actually is around Little Rock. It was around I think it was 4 minutes 10 seconds. I think the most time in Indiana, it's maybe around 4 minutes 2 to 3 seconds. But still, 4 minutes is a lot of time. But we are not anywhere near that. You got to be right. And I'll show the central part of the line too, so you can see what this is. We'll be able to hop on. And I'm going to give you a link so that you can literally go to your backyard, click on it, and see how much time you have in totality. But Crawfordsville, although most days of the year, this is the place to be. Honestly, if you can be somewhere else closer to the central line of totality, it would be wiser for you. But again, weather's also going to dictate that as well. If we are the only spot that has clear skies, I'd rather be here and only get 30 seconds of totality.
All right, Gina wants to know where is the spot in Mexico that you showed is the greatest eclipse time?
Off the top of my head, I don't know it, but we can take a look at it later when we get to the map. So I honestly, off the top, knowing I'm not going to be there, I didn't really look where that was. I apologize. Are we good to move on, or?
According to the chat, yep.
Okay, but one quick question I want to ask you guys then, knowing that these were 54 years apart, when is the next, and a month, when is the next eclipse going to occur that is of this particular ilk? The 54 years away, May 11th of 2078. We're getting, notice the shape is slightly different. We're not in Indiana again, but we weren't before anyway on the one prior to this. You might ask yourself, excuse me, you might ask yourself, why does the shape change? First of all, they're all ascending nodes. We can see them going from southwest up to northeast, but the shape changes because the tilt of Earth's axis at different times in the year, different months, it's tilted either toward the sun, away from the sun, sideways. So that just that tilt and the time of day that it occurs can cause the path to change shape. I mean, it's really, it's moving along a curved surface here. It's really moving along in a straight line. The moon is in front of the sun. So let's start getting down to brass tacks here. Let's talk about this eclipse. This is a map that shows the amount of time that you get in totality. Bloomington gets 4 minutes 2 seconds, Evansville 3 minutes 5, Terre Haute 2 minutes 53, Muncie 3:46, and so forth. That's all great. But suppose we want to do better than that, and we absolutely can. So this is a free website. It's a Google map. We're going to click on this guy. We can zoom in. So looks like it looks like they're showing Durango, Mexico. That's where they're talking about, because that point is the location where they say that's the sweet spot of the eclipse, the best place to view it. Okay.
I've got another question. Are the varying lengths of time of totality on the center of the path because of the Earth's curvature?
Yes, that is a big part of it. The curve that it's following across the Earth at that time, coupled with the rotation. So the rotation plus that curvature changes the speed a little bit. I'm going to zoom in on something. You give us a little bit of that information. So let's come into good old Seville. So this is exactly what Professor McKinney was talking about for Crawfordsville. That is the edge of totality right there. Okay. Wabash College, good. Motels north of town, not good. The hospital, in fact, is not in totality. That's how close we are to the edge. And when you really compare that to, this is the center line where you get the most totality, we are much closer to being out of the eclipse than we are to being in a really good location for time. But let's just do a quick look here. We're going to zoom in because on campus, what we're going to do is we're going to get together on the stadium. And yes, you can zoom really far. And when I say you can land in your backyard, you can literally go to your backyard and click on this spot. And what it tells me is that the total solar eclipse for us will last for 53.1 seconds at our location. It says, though lunar limb corrected, 30.9 seconds, 31 seconds. I'll talk about that later because that's truly the safe number for looking at the sun without eclipse glasses on. This 53.
Are you able to post this map link, the interactive one, into the chat here?
I can do it before we get out, but
Okay.
I can't. I'm not sure I can do it while I'm talking. I don't know.
Okay.
I'll do it real quick.
So just a few things. The start of the eclipse. Well, we're going to talk about each one of these stages in a minute. C1 starts. This is at universal time. So what we have to do is we have to consider that we have to subtract 4 hours from that because this is from Greenwich, England, the prime meridian. So what we've got here is this is really then 1349, which is 1:49 and 50 seconds. That is when not totality, but partial eclipse. That's when the bite starts being taken out. You can see the little diagram up here that shows that as well. The next step, totality begins. That is at 3:06 and 41 seconds. Maximum eclipse 3:07 and 8 seconds. End of total 3:07 and 34. And at 4:22 and 23 seconds, the show's over. The last bite is taken out. And we're going to step through all of these later, so don't worry if this went by a little bit fast. But those are the little stages that you're going through. And as you see, if you look on the underlying screen, you can see that there's a shadow moving across at each one of these stages, different amounts. So we can see this actually progressing. If we were just to go, let's just say we just went down to, I don't know, let's say Brownsburg. Actually, let's go to Jamestown. Jamestown isn't that far away. If we go to Jamestown, Jamestown gets 2 minutes and 47.9 seconds, 2 minutes and 48 seconds of totality. That's not that far. You know, we're only halfway to Indy at that point. Because we've gone in a direction that allows us to get almost, you know, a perpendicular to this line here, we're going toward totality the quickest. So somewhere in here, Brownsburg gets 3 minutes and 27 seconds of totality. Okay, the actual times are only seconds different because the shadow is moving at 2,000 miles per hour. What's that? Notice the, so this is, when I said 2,000, all right, I'm exaggerating. It's 1,988 miles per hour. I was rounding through, but it's still, it's flying, okay? So this, Dr. McKinney, were you able to get the link in there for folks? Perfect.
I was, yes.
Okay, this is, for once I discovered this, it was almost like finding something that had been buried under the GNC for the last 2,000 years. So, I mean, this is incredible. The lines, when we were asked before, how comfortable are we on this line right here? It hadn't shifted very much along this line. I think what I saw is it may have taken such that the cemetery, all of the cemetery was outside of totality, but that's all the difference that I saw. But it's a fair question because in certain other places, they're showing down in Texas, some of the state parks where people were planning to go view are not supposedly not in totality anymore, simply because a measurement of the size of the sun changed the size of the path and narrowed it up a little bit. So this is hopefully this is something that you guys will find useful to you going forward. You can do it for your home anywhere you go. Now we're going to just step through the phases of the eclipse, and I know we are rapidly running out of time. I turn into a pumpkin at a certain point. So these are the phases that you would see for a total solar eclipse. And what we've got in this situation, remember that this is occurring over the course of about 2.5 hours, and it starts when the sun is at its highest point in the sky. Now, this is exaggerated. This is a different eclipse, so the sun's not going to be this low when it's over, but it is going to be dropping down over time. When it starts, we'll see a little bite, then a little bit more of a bite. The moon has moved over the sun. The earth has rotated, so the sun has shifted in the sky as well. There's a lot of stuff going on here. More and more bite, then we see this, and then it reverses. I'm going to go through these steps as well. So this is the time of totality. This is the time when you would take your glasses off. The very first point when a bite is taken out is called first contact. So that first contact, when we looked at the simulation from before, that Google map, 1:49 and 51 seconds. It's going to be kind of hard to see here, but in this location, the moon is right here. It's just touching the sun, just starting to move in front of it. We'll see a bite taken out, larger and larger bite taken out over time. Some of the eclipse itself is an incredible thing to see, okay? Even though I've never been in totality, I've gotten to witness some of these other things that go on, other phenomena that happen during the partial phases. First of all, the temperature is going to change. It's going to get cooler. Now, it takes a while for Earth to heat up and cool down, so there's going to be a bit of a lag, and it's not going to drop a lot, but it could drop 5 to 10 degrees over the course of the eclipse going to totality, and then lag behind maybe 15 minutes or so, still getting a little cooler, and then start warming up. So we'll notice those things. The sun, looking at a crescent sun, if you have your eclipse glasses on, as long as they are on, you can take a look at the sun. These have to be approved eclipse glasses that we'll talk about later. But if you have those, you can look at the sun. But for safe viewing, there's indirect ways you can do that. You can do pinhole projection. Make a little pin in a piece of paper, a piece of foil. Put that on the end of a shoebox and let the light shine into the backside of a shoebox onto a white sheet of paper. You'll see the sun being projected on there. It'll be flipped upside down. But when you see that, you'll see a bite taken larger and larger out. This is a great way for kids to look at it. That way you don't have to worry as much about them looking up at the sun or taking their glasses off or something like that. This doesn't require any of that. We have natural pinholes when you have trees with leaves on them. And unfortunately, we don't have a lot of leaves around here right now. What we have is snow if you're not in the region. This is what we're getting for fun tonight. But with if you do have enough leaves on the trees, there's little pinholes just where the leaves are not completely covering up sunlight. You'll actually see that the shapes are going to be crescent shaped. So that's something you should just pay attention to. Pay attention to your environment around you. Shadows are going to look weird. When we say weird, what actually happens is, since the sun is not going to look like a disc anymore in the sky, it's going to start looking like, you know, a moon, a crescent moon. Well, as it gets thin in one direction, but it's still long in the other direction, what you'll end up getting is sharp shadows along the length and fuzzy shadows the other direction. So if you actually have something that'll project the sun itself so you can see that crescent shape, you can rotate a piece of paper. Just cut it into a shape of an L, like a piece of cardboard or something like that, to cast a shadow. Thinner is better on this, but you don't want it too floppy. You want to make sure that it, you know, kind of hold its shape. But if you align the crescent along here, you'll get the sharp. Along here, you get the fuzzy. Our shadows from the sun are fuzzy all the time. We just don't notice it until we have something to compare it to that is sharp, and it is striking. There's also an effect called the Purkinje effect, where we say colors look weird. Well, the way our eyes behaved in color vision using the cones, sensitive to red and green, but as light gets dimmer, our eyes shift to vision with the rods. Well, the rods are sensitive. Basically, we call that our black-white vision, or our non-color vision. But the reality is, green is the color that those pick up more. We just end up perceiving those as different shades of gray. What you should be able to see is the reds start to fade, but the greens will pop. We are on the Wabash football field, which is green with a big red W on it. I am very excited to see what this is going to look like as we progress through the eclipse. Addition, animals are going to behave differently. They're going to start acting like it's a sunset. Birds will start flying to wherever they nest. Chickens will go to roost. You'll hear crickets. Bees are a really interesting phenomenon, because bees tend to try to get to their hives as sunset is coming. Well, this is happening a lot faster than what they're used to. So you'll see a lot of activity at hives where bees are returning. But also, if bees realize they're too far away to get back, they'll essentially drop and wait until what they think is morning. Fortunately, they don't have that long to wait until the sun comes back out. So all of these kind of things, shadow bands, I'm going to simply skip right now, because it's one of those things that is really difficult to see. But here's what I will promise you. If we are able to see shadow bands and photograph them, I will add something on in an email later for you guys to see these things. But I'm told that is a really interesting phenomenon. So now we're at totality, second contact, 3:06 and 41 seconds. The sun should, or the moon should cover up the sun. It goes through a couple of stages just at the end. Remember, the moon isn't perfectly smooth. So we got mountains on the moon, we got craters. So the sunlight's going to peek out a little bit, just as, we imagine the moon is moving this direction, okay? So we see a little bit peeking out, something called Bailey's beads, which look like little beads of sunlight peeking around. And then what's referred to as a diamond ring effect may be seen as well. And then we pop into totality. This is the time. Once this happens, you can take off your eclipse glasses and look at the sky, but not until this, okay? Once that's happened, it's safe to take the glasses off and take a look up, and you should do that. But you need to be very cautious, because you're not going to be able to leave them off for long. You need somebody who's paying attention to the time, okay? Talk about how you do that a little bit later. What might you see? Well, depending on the sky conditions, we might be able to see the outer layers of the sun. This is called the corona, the outer atmosphere. It goes much farther than the sun's body. In fact, it gets very dim out here, but that's only because it's not very dense. The interesting thing is, although the surface of the sun is only 6,000 degrees, this part of the sun is more than a million degrees. NASA is actually launching different, not launching, but they're sending up planes. They're going to be flying at 60,000 feet to study the corona at this point, because they want to try to, we've got new equipment with more sensitive detection techniques, and we're going to try to look to see how in the world, we still don't fully understand how you can have something that's farther away from the sun but is a million degrees compared to the sun's surface. So they're going to try to study that. You're not going to see it quite this bright. In fact, probably not nearly this bright. But if folks are taking photographs around you, this is one of the things they're going to want to look at. In addition, there are other objects in the sky that we'll be able to see. And I'm going to stop sharing and let Professor McKinney run through another simulation here of what it will be visible for you.
Okay, so the image that Dr. Ross showed a minute ago was made with Stellarium. This is a piece of software that's free, open source. You can download it. There's even like a mobile and iPad version, but it's really handy in terms of teaching. So what I've got here is I've got this tuned up to maybe an hour or so before totality. And what we can kind of see is we've got the moon right there and the sun right here. And as if I advance time minute by minute, then of course the Earth is rotating. And so that's why those lines are moving, because those are, I've got the green lines that are sort of in the background are tied to the compass direction. And so as we get into, 2 o'clock, we're sort of halfway through. And then, by the way, I've set the location of this for Crawfordsville. So you've got in this software, you can configure down your exact location, latitude and longitude. And so as we get closer to just after 1500, then we would be right, about there. So 1506, 1507 when we're in totality. But one of the things that'll be interesting is even though there will still be some light that you'll be able to see, it's not going to be enough to obscure all of the other celestial bodies that you normally can only see at night. So actually, we'll have quite the show in terms of the other planets and stuff. We've got Jupiter, Venus, Saturn, Mars, and that'll be naked eye visible from here in Crawfordsville, assuming, of course, the weather's good. But you'll be able to see those. And the other thing I'll maybe just mention briefly is that if you've got a star that's very, very close to where the eclipse is going to occur, this was actually done a little over 100 years ago by Arthur Eddington, an experiment that if you viewed the sun and a star and their relative distance from each other, angular distance, at multiple locations, then if it was really close to where an eclipse was, then you'd actually be able to see it, even though you wouldn't normally be able to, because the sun would there'd be too much light from the sun. But during an eclipse, you get that moment of darkness, and the angular difference, you could actually measure that, and that is one of the first experimental verifications of relativity, was basically that the light beam, or where you observe the object in the sky, gets bent by the sun, and it's so close that that's measurable. So yeah, that's basically what we'll see. And then of course, as time goes on, then when the show's over, then everything will kind of recede off the opposite direction. And, at that point, it won't be safe to have the eclipse glasses off, but it'll essentially be the exact same as the hour and a half or so before, just everything in reverse order. Okay. So like I said, yeah, this is Stellarium, this software, and it's really handy. Dr. Ross uses it with his astronomy students in the lab. And I use it for teaching spherical trigonometry when I get to do that. All right.
All right.
Back to you, Dr. Ross.
Very good. All right, we are in the home stretch here. So this shows that view, which probably is a little closer to the way the sky would look. You're still going to have that blue color. I did notice a question from Professor Gunther that says, "Is it safe?" So yes, during this time, it's safe to take a look at the sky without your glasses. And this, otherwise, you would not be able to see these objects: Jupiter, Moon, again, Sun and Moon on top of each other, Venus, Saturn, Mars. It's doubtful you're going to see these. It's just going to be too faint. They're about 20 degrees from the west southwestern horizon. But Jupiter ought to be visible. Venus ought to be visible. And there is a comet that is working its way around right now, and it may be, I mean, we know where it's going to be. The question is, it may be bright enough. If it's outgassing because it's near the sun at this point, it may have brightened up. In fact, I just read something earlier this evening that it is now a naked eye object in the sky. If that continues on for the next few days, we may be able to see that during the eclipse as well. So, but again, you only do this during totality. And so this is where we get into the question of, all right, so how long can we look at this? Third contact is 3:07 and 34 seconds. So remember, we said that was 53 seconds that you should have for totality, and then the eclipse should reverse itself. In most locations, if you look up the time of totality and the time between second contact and third contact, you're fine. You're safe during that entire time. Here, unfortunately, that's not the case. We're too close to the edge of totality. And the reason for this is something they call a limb correction or limb effects for the moon. Because you have mountains and craters on the moon, and because it has a rough shape, notice that over here on this side, it's sticking farther out than what would be a standard circle. But on this side, it's actually cut in a little bit. Okay, the problem with that is, since the moon is moving across in this direction, even though theoretically in totality you should be covered up front and back end, the sun's peeking around the side through here. We only have 31 seconds truly of safe viewing. So that's something to keep in mind. If you are in Crawfordsville or another place that's near the line of totality, then, or near the edge of totality, you need to consider what is that limb corrected time. If if the sun peeks back out, all you do, if you've missed it, just look away immediately. The main thing is make sure that you're watching out for kids, because your pupils have dilated at this point. You're letting in a lot of light. You're dark adapted. This has happened over time. If you've been standing out there and then all of a sudden this sunlight starts coming out, you could do permanent eye damage. So you need to be very cautious. In most places, though, like if we were talking about Jamestown or any of those other areas, if you're more than just a few miles away from the edge of totality, there is no limb correction to worry about. Okay, you're shifted enough. The moon is shifted enough that direction to completely cover up the sun on that side, so you're safe. But if that software that we sent the link to, it will tell you this. So it's worth the price of admission for tonight's discussion just to know that. Fourth contact. So between the third contact, the end of totality, and the actual end of the eclipse, which is at 4:22:23, you're going to have things reverse. You'll start seeing animals return to their normal behavior. You'll feel things differently outside. The warmth will return. I heard on the weather tonight that we're supposed to be 70 degrees that day. So if it's 70 and sunny, that is a perfect day for viewing this eclipse. We hope that it will be like that. We'll start seeing that temperature come back up. some important information. First of all, eclipse glasses. We said you have to have these on at all times when looking directly at the sun, unless it's during totality, and that's a very small amount of time. I mean, even if you're in a perfect right in the center of the line and you're at 4 minutes, it's only 4 minutes out of the entire 2.5 hours of the eclipse. Every other time, if you're looking up at the sky, you have to have approved eclipse glasses. These should have stamped on them ISO 12312-2, filters for direct observation of the sun. Unfortunately, there are counterfeit versions that are out there, and we have to be cautious about that. There are reputable dealers that are listed on the American Astronomical Society website, vendors that sell these. But if you were to buying these from online at Amazon, I would be a little bit concerned about, unless you could verify the distributor. But a place like, I think, Walmart or Kroger, someplace like that, I think they would have vetted their vendors, so you should be safe. But this is what has to be stamped on there. Unfortunately, if somebody's selling counterfeit lenses, they'll also stamp this on there. I mean, if you're going to steal, you're also going to lie. So, again, here we only get 30 seconds of safety looking at the eclipse without our glasses. Most of the rest of the time, you have to have them on. All of the rest of the time, you have to have them on. And lastly, this is something that I've been asked in the past about welding helmets, welding glasses. Some welding glass is okay, but the vast majority isn't. It's not made, it's made for flashes, but it's not made for continuous viewing. So you need to be careful of that. I would just err on the side of caution and say, don't use a welding helmet or welding glasses. Most likely, they're not going to be approved for this. Let's suppose the weather stinks. Let's suppose wherever we are, things aren't good. When is our next opportunity in the continental U.S.? August 12th of 2045 is this eclipse right here. Notice that would be a descending node as we're coming through like that. So we would see this come across through the west central part of the U.S., come in through my old home state of Arkansas, and then head down through Florida. My guess is there will be a lot of folks reserving rooms in Florida around that time. Suppose you say, oh, I can't make that one. I'll wait for one that's in Indiana. You got a little bit of a wait. September 14th, 2099. Okay, here it is right here. Notice it doesn't even come through Crawfordsville. It's Indiana. You're still going to have to travel. Okay, but it's notice also, though, that's 2045, 2099. That is 54 years apart, 54 years, 33 days. It's the same Saros. It's also a descending node. Okay, so to wrap this up on my end, these are some of the resources that we used in pulling this together. This is the website that I used for Google. This will get you to the Google Map website. This gentleman right here is the one. He has been mapping eclipses on Google Maps for years and is highly respected and trusted. He also relies on some of these other people to pull in his information. If you want to make a purchase of something, that I always tell my students, don't buy apps. There's always a free version of something that's worth it. This is one of the only times I'm going to talk against that. There's a timer, a solar eclipse timer, that is $1.99, the app for your cell phone. And I'll click on it here. What this does is it will talk you, I mean, literally talk you through the eclipse. So if you tap wherever you are, it will get your GPS location. Then you click calculate contact times. It will tell you when C1, C2, C3, C4 occur, so you can plan for those. It will also talk you through various things. It will say such things as pay attention to animals at this time. Pay attention to the temperature. Get ready for totality. And it will do a countdown. I'm actually using this on the football field with Dr. McKinney. We're going to make sure that we're doing everything safely with the folks that are around us. but I'm going to use this to guide me through. You can adjust the contact times on this for the limb correction. So I'm going to do that as well. So this is for $1.99, you can't beat it. Okay. And I don't get anything out of this. I just thought this is one of the most useful things I've ever seen for $1.99. So with that, I'm going to wrap up my part. Professor McKinney, what would you like to add?
Just that if you've got any friends who are Illuminati that have their hands on the weather control buttons for the day, then maybe do send them a box of cookies or something. We're really every time I look at the forecast for Monday, yesterday I looked at it sunny and clear. Today I looked at it partly cloudy. I've given up looking, right? I'm just going to wait and see what we get on Monday. Our plan is that if we have if the weather is really miserable, then we're going to be in Salter Hall and we'll have NASA's coverage. NASA has stationed people all along the path of totality and are going to have a lot of really, really neat coverage. They did the same thing in 2017 and it was really first rate. But if it's cloudy, partly cloudy, puffy or something, then I think we'll still have everybody outside, because even if you don't see the totality part of it and the sun at that point, you might still be able to see Jupiter or Venus, or and you might miss out on you might miss out on the animals doing different things, the different sounds, the sort of hazy, dull colors, all of those things, even if you can't see the sun properly. And that's all I've got. This was a pleasure. I hope you guys enjoyed it. And I think we've probably well run over our time. We've eclipsed our time. Yeah, okay.
But we had
I'll
a lot of
myself
fun,
out
and
now.
we thank you for taking time out of your evening to listen to us, and hopefully you learned a little bit, some of it useful.
Well, thank you both, Dr. Ross and Dr. McKinney. This was wonderful, and we all learned a lot. I do have a couple questions that came into me. Some folks have said, if I drive to Wabash, do I have to buy a ticket to get into the stadium? No, you don't have to buy a ticket, but we do ask that you bring your own glasses if you're not Wabash faculty, staff, or students. We will have enough glasses for the first 900 faculty, staff, and students. But if you are, like there's a woman on my team who's bringing her kids, she knows she has to bring her own glasses for her kids, because we really have to limit those to our students and faculty and staff. But otherwise, the more the merrier. Please drive safely though. Indianapolis and other counties locally have already issued states of emergency preemptively for the roads. My brother's down in Bloomington and they are predicting 75-mile backups on the roads leading into and out of the city of Bloomington, Indiana, because folks are already traveling in for the eclipse. So if you are planning to come join us in Crawfordsville, plan ahead and do so safely. I don't want any of our friends stuck on 74 and completely missing the sun, because that would be miserable. The other thing is I had a lot of folks request permission to record this presentation on their own computers. I rejected those requests because I am recording, and I will do my darndest to get this video recording edited and posted on the Wabash YouTube page by tomorrow. But if I can't make tomorrow, then by the end of day Friday. That way we all have the weekend to check back over these links, watch it with our family. I know I'm going to send it to my dad. I'll find it really cool. So we want to make sure that you have all of that information by Monday. Professors, is there anything else? I'm happy to help facilitate emails if you have anything you want to send out to our guests tonight before the eclipse. Let me know. Otherwise, I think that's the end of my housekeeping spiel. If you guys have anything final to say.
Yeah. The question about coming to Crawfordsville, if you're going to be traveling and you're doing it early enough that hopefully the roads won't be too crazy, keep going past Crawfordsville. I mean, seriously, right? Getting just to Linden or not Linden, Ladoga.
Ladoga.
Sorry,
Mhm.
yeah, wrong direction. Don't go to Linden either.
Don't go to Linden,
Right.
you will not be in totality
Right.
at all.
Great ice
You'll be
cream,
very sad.
lousy
Yes,
Eclipse.
the Lindy Freeze is wonderful. A plug for
Yeah,
them.
but not for the Eclipse. Yeah, even if you were going to go to Ladoga, you're talking several minutes of totality, and it is literally just down the road. So this is one reason we haven't really advertised the on-campus activities to a broader audience, because again, anybody traveling should just probably go a little further. If you're, people in Crawfordsville, we are kind of expecting to get some foot traffic. All of the local schools have actually canceled school that day and are doing e-learning because we're very concerned about the traffic through the county. The hotels, of course, are all booked up solid. The emergency management people are worried about gas shortages and grocery store shortages and bottled water shortages and things like that, as just hordes of people descend on the area. And I remember in 2017 there were some really long traffic lines, a lot of chaos, and a lot of counties have, our emergency management folks here in Montgomery County, for example, have been talking to counties and other agencies that were in the path of totality during the last eclipse to say, okay, what do we need to know to be ready for this thing? And there is actually one sort of small spot that is in the path of both this one and the 2017 eclipse. They've really got it made. They got lucky. They're getting two for the price of one.
Carbondale, Illinois.
Yeah.
So yeah, it crosses right through there.
Hey, professors, do you have time? Last question. Do you mind talking briefly about the reds and the greens in Little Giant Stadium?
Yeah, I saw that, and not at all. In fact, it reminded me of something else I wanted to add. So what you should see over time is simply that the red, everything's going to get dimmer, just like it does at dusk. But what we're going to see with that colors, because this happens in such a time that we can really pay attention to it. What you will notice if you're paying attention is that the reds will fade more quickly than, say, the greens will. So although everything is getting dimmer, the colors will shift. So what we are actually recommending that people do is wear bright colors on Eclipse Day. And they don't have to be reds and greens, although I happen to have a young man and a lady sitting next to each other at a talk the other day, and one was wearing a green sweatshirt and the other was wearing a red shirt, and I'm like, you two have to be together on Eclipse Day. Okay, so the same thing. I even see somebody that's got 3D glasses on right now. I think those will be awesome. The reds and the greens, simply that shift. So, but it doesn't have to be reds and greens. It can be combinations of other colors, but bright colors should start to fade, and you should see a dimming of the reds compared to others. So that's really what we're looking at. Does that get what we need?
Yeah, she's nodding. Yep.
All right, awesome.
All right, cool. Well, thank you both so much. If no other words of sciencey wisdom, then I will wrap this up so I can go to bed and then start editing at 8 a.m. tomorrow and get this out into everyone's hands.
No, just stay up all night tonight. It'll be great.
I thought about it, but there's a big fundraising day that Wabash traditionally does at the end of April every year, and I'm planning that this year. So I need to get at least like 3 hours of sleep. But
okay, so since we're on here and you got that plug in, everybody that's on this Zoom call needs to donate. All right, if you got something out of this, pay it forward.
Well, thank you. I'm not going to say that the day of giving is April 24th, but I'm not saying it's April 24th. So
exactly.
Yep, it's our best. It's our, what do we call it? The best, the worst, best kept secret, the best, worst kept secret, whatever. My boss has a term for it.
Yeah, it's totally zero coincidence that happens to be President Scott Feller's birthday.
It literally is a coincidence. We've never. No, it is. I swear on the
I'm
eclipse.
joking.
I don't know. I can't think of. I don't want to bring religion into it, but
yeah. But if the eclipse doesn't occur, we know what's happened now. So
exactly.
Thanks everybody. We really appreciate you.
Oh, sorry. One last question. Mark wants.
Sure.
Oh, you got it.
I got it. Okay.
Professor McKinney. Professor McKinney, for those of us who don't speak science, what is 1440? Is that 2:40?
2:40 p.m. Yeah.
2:40
so
p.m.
we actually have a special class schedule for the afternoon, and afternoon classes, there's a little window around the eclipse. So everybody will get released from their what normally would be 1410 classes at 1440. And then we'll have about 40 minutes for the eclipse, a little bit more on the beforehand and then a little bit less on the aftermath. But that's what we're doing. Unlike a certain unnamed university, alleged university of the South, we're not canceling class.
We didn't close our offices either, so we'll all be there
Right.
Monday.
All right, folks,
It'll be
keep your
fun.
fingers crossed for clear skies.
Thank you both so much. This was such a joy.
Thank you.
Thanks, everyone. Good night.
Good night.